Greetings, it's Paul Bamberg welcoming you to the introductory video for Class 13 of Math 117, in which we are going to run through the very challenging dominated convergence theorem. Our major goal is to remove the requirement that our random variable x be positive. And in order to do this, we're going to write a random variable x that can assume either positive or negative values as the difference of two positive random variables, x plus and x minus. So if we write x equals x plus minus x minus, then x will be integrable if these individual random variables are integrable. And furthermore, the expectation of x is just going to be the difference between the expectations of x plus and x minus, respectively. We can write this in our standard integral notation. And there are a lot of properties of this random variable x that follow immediately from what we know about positive random variables. First, and this is something that's true whether or not x turns out to be integrable, we can write x as a pointwise limit of simple random variables, where we make the simple random variable x sub n by simply forbidding it to have any value greater than plus n and any value less than minus n. In other words, we make the absolute value of x sub n be less than or equal to we achieve the fact that the absolute value of x sub n is always less than or equal to the absolute value of x. If x is integrable, it's because x plus and x minus are integrable. And if we take the sum rather than the difference of x plus and x minus, we're calculating the expectation of the absolute value of x. So a condition for x to be integrable is that its absolute value has to be integrable. And in that case, the absolute value of the expectation is less than or equal to the expectation of the absolute value. If we look just at absolute values, so we're talking again about positive random variables, then as you already know, the smaller of two random variables is integrable if the larger of the two is. Finally, if we find that random variables x and y are integrable, so are their sums, so is a scalar multiple of either of them. That is, they form a vector space, and the usual name for this vector space is big L1. Now, in the very common case where the image of x is a countable set, you can calculate the expectation of x by summing an infinite series. This will be an infinite series that will have both positive and negative terms if x can assume both positive and negative values. But the expectations only define if the series is absolutely convergent. If the infinite series that you sum is only conditionally convergent, then we say that the expectation of x is undefined, even though the series that we would use to compute it may be conditionally convergent. Now let's think a little bit more about bounded sequences of real numbers. So far, what we've been doing is to consider sequences of random variables where the values for individual events in the sample space are increasing sequences of real numbers. And as you know, for an increasing sequence of real numbers, there are two possibilities. Either it's unbounded, in which case we say the limit is plus infinity, or it's bounded, in which case the limit is the least upper bound. But now that we've removed our requirement that our random variables be positive, we have to consider some slightly more general sequences. So let's look at an example, and you can see what I've done here. I have taken a sequence that is 1/2, 3/4, 7/8. I mix that in with a sequence 1/4, 1/8, 1/16, and so on. That's a subsequence that converges to 0. And then I've mixed in -1, -2, -3. That's a subsequence that converges to negative infinity. Nonetheless, this sequence does have an upper bound. You've probably already perceived the upper bound is 1. More generally, there are two possibilities. Very frequently, there is a specific element in the sequence that is at least as great as any other element of the sequence, and in that case, that individual element is the least upper bound. If, for example, I simply remove this minus sign and make the second term be 1 rather than -1, 1 is the least upper bound for the entire sequence. If that doesn't happen, then I can extract an increasing subsequence that has the value capital M as its upper bound. In this case, that sequence would be 1/2, 3/4, 7/8, and so on, which converges to the upper bound 1 of the entire sequence. In any event, if a sequence is bounded above, it has a least upper bound. If a sequence is bounded below, it has a greatest lower bound. Now, you may have seen these concepts before, in which case you were probably puzzled by them, or you may not have seen them before, in which case you were lucky, but you can't stay lucky forever. You're going to have to learn about lim sup and lim inf. So this requires some careful thought. Let's think of the tail of the sequence. That is, the sequence starting with just the nth element. If we have a bounded sequence, then this tail has an upper bound. It's the supremum of the mth elements for all m that are greater than or equal to little n. And this quantity can only decrease as n increases. It will decrease, for example, if the mth element is in fact the largest element of the entire sequence, the effect of which would be once we go beyond m and consider the tail starting with the m plus first element, for example, the upper bound must necessarily be smaller. Similarly, if you look at the tail of the sequence and ask yourself about the infimum, that infimum can only go up as you go farther along in the sequence. So you have a decreasing sequence of suprema, you have an increasing sequence of infima. Both of these are bounded sequences, and their limits are known as the lim sup for the supremum and lim inf for the infimum. If these are equal, then the series converges, and it converges to their common value. But these quantities exist for any bounded sequence of real numbers, whether it converges or not. Once you recognize that, you've got a rather easy proof of the famous Bolzano-Weierstrass theorem, which says that every bounded sequence of real numbers has a convergent subsequence. Here's how the proof goes. Let's think about the tail of the sequence, what we get starting with the nth term for m greater than or equal to n. This always has an upper bound, and since the upper bound, the supremum, necessarily decreases as m gets larger and larger, this upper bound cannot be less than the lim sup of the sequence, which I will call capital M. Now there are two cases. The first possibility is that this supremum is always equal to a specific element of the tail. An example will make this situation clear. If I start here then the supremum is 2. If I move along to here, the supremum is 3/2. If I move along further, it's 5/4, and so on and so on. And these specific elements form a decreasing subsequence whose limit is m. That's case 1. However, it's entirely possible that we reach a point in the sequence where the supremum is not equal to any specific element in the tail of the sequence, in which case it's stuck at the value m, and in that case we can construct a subsequence that increases to m. Here's an example of that. We go long for a while, and now we have 1/2, 3/4, 7/8. We will never find another element like this 2 that was the largest element of the tail, but we will have an increasing subsequence, in this case a subsequence whose limit is m equals 1. Now I need either to introduce you to or remind you about Cauchy sequences. Cauchy sequences are ones that, in the case of real numbers, converge, but that can be characterized without talking about the number to which they converge. All we have to say is that if we go far enough along in the sequence, all the terms get closer and closer together, or to be precise, you give me any positive epsilon, I can specify an integer n0 with the property that if we go beyond the n0 term to get two different terms, an and am, the absolute value of their difference is less than epsilon. Or you can say, as I let m and n both go to infinity, the difference between the values of two consecutive terms, the absolute value of that difference goes to 0. It's very easy to prove that every convergent sequence is Cauchy, and it's not hard in the case of real numbers. You have to use the Bolzano-Weierstrass theorem to prove that a Cauchy sequence of real numbers is convergent. Now, finally, I can state the dominated convergence theorem. We've got a sequence of random variables that converges almost surely to x. I like to think of this sequence of random variables as representing a sequence of payoff functions day by day, and converges almost surely means there may be some elements in the sample space for which this sequence of payoff functions doesn't converge to x, but we can more or less ignore those because they are a set whose probability is 0. What does dominated mean? Dominated means there is some integrable random variable, one whose expectation we can calculate, with the property that the absolute value of the nth payoff function is always less than y, except perhaps on a set of measure 0. And what the theorem says in this case is each x sub n has to be integrable. Furthermore, the limit x has to be integrable. And finally, the limit of the expectation of x sub n is equal to the expectation of x. In order to prove this, I'm first going to have to prove a result known as Fatou's lemma. So let's get started on that. Given an arbitrary sequence of real numbers, we found a way of creating a non-decreasing sequence of real numbers. What we do is we look at the tail of the sequence going on from the nth element. We look at the smallest value that can be achieved. Think of that as the worst payoff you can ever get. This quantity can never get smaller, so it forms a non-decreasing sequence of real numbers. Non-decreasing because it could, in principle, stay constant. It doesn't actually have to increase. And what this converges to is, by definition, the lim inf of the sequence. I remind you that the same phenomenon occurs in this case that we saw recently with Suprema, the numbers may form a subsequence of the original sequence. If you look at this sequence and ask yourself, what is the lim inf? You can say, well, if we go this far, the smallest payoff we can ever get is 3/4. But if we go to here, the smallest payoff we can ever get is 7/8. So the numbers in the sequence of infima, 3/4, 7/8, and so on, are an actual subsequence of the original sequence. But that's not necessarily so. If you look at this case, you say, well, what's the worst payoff we can get beyond here? Well, the payoff still has to be positive. It's 0. Go along here. What's the worst payoff we can get? It's still 0. So the sequence of infima in this second case is 0, 0, 0, 0, 0, and there is no 0 in the sequence. Now let's try doing the same thing, not with real numbers, but with random variables. So what I'm going to do is consider a sequence of random variables, and from the sequence of random variables x sub m, I'm going to construct a new random variable z sub n. How do we construct this? We look at any element in the sample space, anything that can happen, and we ask ourselves, what is the smallest possible payoff beyond the payoff on the nth day? And we define that to be z sub n of omega. Why does this work? It works because we are only considering positive random variables. Positive random variables are bounded below by 0. So the worst imaginable payoff is 0. Now, you'll recall that the Borel sigma field can be generated by open sets that run from -infinity to a, and therefore an inverse image for such a set, the subset of the sample space that leads to a payoff of less than a on day m, is in our sigma field. And if we take the union of that over all values of m that are greater than or equal to m, that is, if we consider events in the sample space that pay less than a on some day, either day n or beyond, that's also in the sigma field. But what's that? That is the inverse image of under Zn of the Borel set that runs from -infinity to a. It's the set of events for which the lowest payoff that you can get on or after day n is less than the value a. And now I can prove Fatou's lemma. I've constructed this worst payoff for each point in the sample space random variable. Each of these z sub n's is measurable, that is, the inverse image of a Borel set is in the sigma field. Since these are necessarily less than or equal to the corresponding x's and positive, and the x sub n's are integrable, so is each z sub n. And finally, this z sub n, being a sequence of infima, is an increasing sequence, and what it converges to is the lim inf of the original random variables. So we've got an increasing sequence of integrable random variables. They're all measurable. Apply the monotone convergence theorem, and we conclude that the limit of the expectation of z sub n has to be the expectation of the limit, the expectation of the lim inf of x sub n. But z sub n is always less than or equal to x sub n, so I can turn this into an inequality by replacing z by x. And finally, I can say, in the case we're interested in, where x sub n converges to x, except perhaps on a set of measure 0, so it's almost sure convergence, then the lim inf of the x sub n's also converges to x. Remember that if a sequence converges, its limit is equal both to its lim sup and its lim inf. And so finally, by the monotone convergence theorem, I can say that the lim inf of the expectation of x sub m is greater than or equal to the expectation of x. And you look at this and say, have you made a mistake, Paul? It looks as though you've got your inequality the wrong way around. It looks to me as though the lim inf should be less than or equal to the expectation of x. Well, that second statement is true, but the reason we've got a proof is that we are now going to have this inequality both ways round, establishing equality. Okay, now that we've got Fatou's lemma, we can cleverly apply it below as well as above. So previously we've been looking at the infimum of a tail. Now we're going to look at the supremum of a tail. We're going to construct a new random variable wn, which is the largest value of x sub n beyond the nth term for each point in the sample space. Previously we constructed an increasing sequence. This time we've constructed a decreasing sequence, and it converges almost surely to x. Recall that we have, by the hypotheses of the dominated convergence theorem, a random variable y that dominates all the x sub n's. If it dominates the x sub n's, it dominates any supremum, w sub n, and therefore y minus w sub n is positive, and since the w sub n's are a decreasing sequence, this difference is an increasing sequence, and it converges to y minus x. I'm just going to stop saying almost surely. So, by the monotone convergence theorem, the expectation of y minus x must equal the limit of the expectation of y minus w. I split up the two terms, and I notice we've got the expectation of y on both sides. I can cancel that out and say what I've shown is that the expectation of x is equal to the limit of the expectation of the w sub n's, but since the w sub n's are necessarily suprema of x sub n's, then this is going to be greater than or equal to the lim sup of x sub n. Now what have we got? We've got the lim inf greater than or equal to the expectation of x, and in turn, another of these backwards-looking inequalities, that's greater than or equal to the lim sup. That's not too surprising. Basically, we were proving Fatou's lemma upside down. Of course, it's true that the lim inf is less than the expectation, is less than or equal to the lim sup, and therefore the limit of the x sub expectations of the x sub n's is the expectation of x. That's the dominated convergence theorem. We did it only for positive random variables, though, so in order to extend this to an arbitrary random variable, what we're going to have to do is apply this theorem separately to the positive part and the negative part. You work some examples of this. It turns out to be rather complicated in practice. So we're starting with some random variable that is not positive. And for the positive part, we invent an increasing sequence of simple random variables. For the negative part, we invent a decreasing sequence of simple random variables. This is our standard strategy. Given an unbounded variable, we try to write it as a sequence of bounded variables, and more generally, given any sequence of random variables, we try to write it as the limit of a sequence of simple random variables. Then if we look at u sub n minus v sub n, which it turns out is not necessarily increasing, but it does converge to x, and the absolute value is less than or equal to the absolute value of x. Here's a trivial example which will introduce you to this complication. The sample space is a sample space with two elements, heads and tails. We're tossing a coin. The random variable is the payoff. You get 2 if the coin comes up heads. You lose 3 if the coin comes up tails. And one possible increasing sequence of simple random variables that's consistent with this is what we do is have 0, 0 on days 1 and 2, 1, 1 on days 3 and 4, and subsequently we pay off 2 for heads. Similarly, for tails, we will lose 0 on day 1, lose 1 on the next 2 days, lose 2 on the next 2 days, and subsequently the loss for a tail will be 3. So we got something that converges to the heads payoff, something that converges to the tails payoff. If you look at u sub n minus v sub n, this is increasing for the heads payoff, it's decreasing for the tails payoff. The absolute value can never exceed 3. However, it is not an increasing sequence. Now finally, we can prove that even for non-positive random variables, expectation is linear. The expectation of a sum is the sum of the expectations. How do we do this? We've got random variables x and y. For x, we have already constructed a sequence of random variables u that converge to the positive part and v that converge to the negative part. We do the same thing, constructing sequences w sub n and z sub n that converge to the positive and negative parts of y. And therefore, we've got a sum of 4 random variables that converges to x plus y. And furthermore, the absolute value of the nth term is less than or equal to the absolute value of x plus y. And wonder of wonders, these are all simple random variables for which we know that the expectation of the sum is the sum of the expectations. Now these 3 sequences are dominated respectively by x plus y absolute value, x absolute value, and y absolute value. And therefore, by the dominated convergence theorem, we know in each case the expectation of the limit is the limit of the expectation. That's what the dominated convergence theorem says. And finally, we can assert that the expectation of x plus y, that is the limit of the expectation of the sum of these 4 terms, is the sum of the limits, and the sum of those limits is going to be e sub x plus the expectation of x plus the expectation of y. Whew, that was a long one, wasn't it?